Hello everybody. We are going to look at linear asymptotes in this lesson. And I do this with my calculus students as part of our curve sketching unit, even though this is almost all pre-cal. I will mention calculus just a little bit, but this is mostly stuff that you should have learned in pre-cal, or maybe you're a pre-cal student and you're finding this. If you want to print the sheet I use for guided notes, you can go to this bit.ly link at the bottom of the page there. So let's talk about linear asymptotes. One thing to keep in mind that they are lines, which is kind of an obvious statement. And so when you write a linear asymptote, remember that as lines, they have to be written in equation form. So either y equals or x equals something. And we're going to start with horizontal asymptotes. And these are typically easier to find before you factor and simplify an expression. And all horizontal asymptotes, because they're horizontal lines, they must be written in the form y equals some constant. And let's see. So the fast way to find horizontal asymptotes, and this applies to rational expressions only. So this is if your function is a fraction of two polynomials, and so that is what a rational expression means. And in these cases, you can compare the degrees of the numerator and denominator, and whichever one's bigger kind of drives the end behavior or the horizontal asymptote. And so there are three different situations. The top degree can be greater than the bottom. The top can be equal to, or the top can be less than the bottom. And these are just memorization rules, but they're pretty efficient. So I'm not a big fan of memorization math, but sometimes it's just more efficient to memorize certain rules so you can quickly get to the answer and start thinking about something else. So if the top degree is greater than the bottom degree, then there is no horizontal asymptote. If the top and bottom degrees are equal, then what is going on? I'm having a hard time here. What just happened here? What is going on? Sorry. Okay, there we go. Okay, so if the top and bottom degrees are equal, then you will divide their leading coefficients. And if the top degree is less than the bottom degree, or you can think of it as the bottom degree is bigger, then your horizontal asymptote will be y equals 0. You have a bottom-heavy fraction in that case. Now, remember, those rules only work for rational expressions, which is where I'm camping out in this lesson. In calculus, we do often have to find horizontal asymptotes for uglier expressions, and it's a longer way, but it's safer to find horizontal asymptotes by actually using limits. And horizontal asymptotes can always be found by looking at the ends of your function. So if you do have a horizontal asymptote, then as you work forever to the right or forever to the left, you will level out. And so we're going to analyze our function as x goes to infinity, and that'll find the right side horizontal asymptote, and you can find the limit. Wow, that was a bad limit symbol. As x goes to negative infinity, because sometimes, depending on what type of function you're looking at, you actually can have a different horizontal asymptote that goes to the left than goes to the right. Now that's only for the calculus. If you're a pre-cal person, then those limits you really don't need to worry about unless you're in an advanced pre-cal and your teacher is actually teaching you calculus. But that's one way to find horizontal asymptotes is by comparing the degrees on top and bottom. And there are other lessons out there about how to divide by the high power of x in the denominator, and you can employ limits to solve it that way as well. But again, I'm looking more at the pre-cal rational expression method in this lesson. Okay, we also have vertical asymptotes. And vertical asymptotes, since they are vertical lines, must be written in the form x equals a number. And when you're dealing with rational expressions, you must make sure you factor all of your expressions first, because if your factors cancel, that creates another situation we have to think about, which is actually removable discontinuity. So that's the next little bullet here. And removable discontinuities are often lazily referred to as holes, which is perfectly fine. I call them holes all the time. And so when a factor does cancel, so if you do factor and you realize you can cancel, say, an x minus 3 on top and bottom, set that factor that canceled equal to 0 and solve for x. That x value will be the x coordinate of the hole. So what I just said, x minus 3 cancels, then x equals 3 will be the location of a hole. But holes will also have a corresponding y coordinate. And so like if I have a function that's continuous and then we just have a little hole right here, that hole does have an x and a y coordinate, and sometimes it helps to know what that y coordinate is. And so what you can do to find the y coordinate is you plug that value of x into the reduced version of your rational expression. So we'll get to do that in a little bit. And then for vertical asymptotes, after you have factored and canceled, if it does cancel, then anything that's left in the denominator, set those expressions equal to 0, and those x-coordinates will give you the equations of the vertical asymptote. And then the last one, which is the trickiest one, and again, I'm only doing linear asymptotes. There are asymptotes that could be like quadratic type asymptotes. And the last one is the slant asymptote, which some people like to call them oblique asymptotes. And these are lines with a defined slope that is not 0, because if your slope was 0, that's a horizontal. So we're talking about linear asymptotes with non-zero slopes. Therefore, all slant asymptotes will be written in y equals mx plus b, or you can go point slope form, but any linear form, and m and b would be numbers, obviously slope and y-intercept. So first, to determine if a rational expression has a slant asymptote at all, you will only have a slant asymptote in your rational expression if your top degree is exactly 1 greater than the bottom degree. So specifically 1 more. Any other difference, then it's no longer a linear asymptote. So make sure the top degree is exactly 1 degree larger than the bottom. And if that is true, then you do have a slant asymptote. And you find the slant asymptote by dividing your denominator into the numerator and then just discarding whatever remainder may exist. So we'll do synthetic division or long division. Long division's safer. It's longer, but it's safer. Synthetic division is really efficient, though. A little suggestion for slant asymptotes: if you can factor and cancel and simplify your expression before doing the division, it helps. You can find slant asymptotes before canceling, but if you factor first, it does make the division a little bit easier. So I have 4 examples where we're going to find all linear asymptotes, and I think the horizontal asymptotes are the easiest, so I'm going to do that first. So my horizontal asymptote, I have a rational expression. My top degree is equal to the bottom degree, so I will divide those coefficients. That is 1x squared and a 2x squared. So the horizontal asymptote is y equals 1/2. I'll go ahead and knock that out before I start factoring and stuff. Now I'm going to simplify this expression as much as I can. The numerator factors to x plus 1, x minus 4. Excuse me. My denominator, if you factor a 2 out, you'll have x squared minus 4, which would factor to x plus 2, x minus 2. And so that means we have nothing canceling. And so my vertical asymptotes, we set each of those factors equal to 0. So we need x plus 2 to equal 0. So we have one vertical asymptote at x equals -2. Set x minus 2 equal to 0. And we have our other vertical asymptote at x equals 2, and there is no slant asymptote. The top degree is equal to the bottom degree. We need the top degree to be 1 more. In the world of rational expressions, you'll never have both a horizontal and a slant. It would be one or the other. Sometimes you don't have either one, but you will never have both a horizontal and a slant. Let's see, number 2. Again, I'm going to start with horizontal asymptote. The degree on top is 1, the degree on bottom is 2, bottom degree bigger. It's bigger on bottom, so that's y equals 0. Which actually just reminded me of an expression my students told me many years ago. With the horizontal asymptotes, if you're bigger on top, if the top degree is bigger, then there's no horizontal asymptotes. So bigger on top, BOT, bigger on top, is undefined. There's no horizontal asymptote. If they're equal, if the top is equal to the bottom, or you could say the bottom equals top, then you divide the coefficients. So if the bottom is equal to the top, you can divide the coefficients. And if the top is less than the bottom, or you could think of that as bigger on bottom, you have a horizontal asymptote of 0. And so the way my students say that is Botu, Betsy, and Bobo, or Betsy, Botu, and Bobu. I don't know how you want to say that. I'm not a big fan of that mnemonic device, but if it works for you, then I guess it works for you. I just remember the rules. So let's see, back to my examples. All right, so back to this. Why's my head right there? So horizontal asymptote was y equals 0 because we were bigger on the bottom. Slant asymptote, there is none, so I guess I'll go ahead and write that. No slant asymptote. I need my top degree to be exactly 1 more than the bottom, and it is not. So now for vertical asymptotes, I need to factor this. The numerator does not factor, so that's x minus 3. The denominator, this is one of those harder ones to factor. I need 3x and x to get 3x squared, 5 and 2, so 5, 2, 5, 2. How about 5, 1? Negative, positive. There we go. Okay, again, nothing canceled, and your vertical asymptotes set each of those factors equal to 0. 3x minus 5 equals 0. X equals 5/3. And x plus 1 equals 0. X equals negative 1. Alrighty. Let's see. Number 3. I can see immediately there's no horizontal asymptote. Top degree is bigger. And if the top degree is bigger, there's no horizontal asymptote. Also, I'm noticing that the top degree is 2 greater than the denominator, which means there's also no slant asymptote. The degree difference needs to be exactly 1, which means there's only horizontal asymptotes. That numerator, x cubed plus 4x minus 1, is not going to factor nicely at all. If it factors, it probably doesn't even factor. I'm not even going to try. If it were x squared, then we'd have a quadratic, and maybe that would factor, but x cubed, not so much. So vertical asymptote, we'll set that denominator equal to 0. It's kind of ugly, but x equals negative 7/2. Here's my vertical asymptote. Cool. And then the last one. Oh, I thought I had a 4. Ah, that's what I did earlier when I glitched earlier. I accidentally deleted number 4. Okay, let me get it back. All right, so here's number 4. And first thing I'm going to do is my horizontal asymptote because it's the easiest. It doesn't require any factoring or anything. So my horizontal asymptote, top degree is bigger, so there's none. Does this factor? Factors of 16 that'll add up to 5? No. 3, 8, and 2 is 6. 4 and 4. No. Okay, so the numerator does not factor, so I don't have to worry about anything canceling. So there's no holes again. I thought one of these would have a hole in it. I guess I just wanted to throw those notes in there. All right. Vertical asymptote is going to be easy. Set that denominator equal to 0. X plus 4 equals 0, and we have a vertical asymptote at negative 4. And this time my top degree is 1 greater than the denominator, so I do have a slant asymptote. And so for my slant asymptote, we need to divide the denominator into the numerator. And if you know synthetic division, good for you, knock it out. It's a heck of a lot faster. It's also easy to mess up just by carelessness. Long division, obviously longer, hence the name, yet safer. So I'm going to go long division. And when we do long division, we're looking at that high power term right there on the outside, and x times 2x will give me the 2x squared. I'll distribute 2x through that, so 2x times x is 2x squared plus 8x. And then we subtract all of that from what's above it. So 2x squared minus 2x squared is 0. That's what I wanted. 5 minus 8 is negative 3x. I'm going to bring down my 8. And I'll repeat. X times negative 3 will give me negative 3x. Distribute the negative 3. Negative 3x minus 12. We'll subtract, and I'm kind of wasting my time at this point. I'll explain why in a second. Negative 3x minus, and that's negative 3x plus 3x is 0. That's what I wanted. 8 plus 12 is 20. And so we do have a remainder of 20. And formally, you would write that as plus 20 over x plus 4. But with these slant asymptotes, we throw away the remainder. And if you want mathematical reasons, because slant asymptotes, we're worried about what's happening as x gets infinitely large, or linear asymptotes is what's happening on the end of our behavior. And as x gets infinitely large, as we work forever to the right or left, that denominator is getting really small. So that 20 over x plus 4 is turning into a 0, leaving you with only the 2x minus 3 for the slant asymptote. So my slant asymptote is going to be y equals 2x minus 3. And there we have our asymptotes. And that is it.